This video is about standard errors. So what's a standard error? It's an estimated standard deviation of a sampling distribution. Okay, and why we would need to estimate that requires some justification. Okay, so let's talk about that part. We have derived properties of estimators in terms of underlying population characteristics. So for example, the standard deviation of the sample mean across possible samples is sigma over root n. N is the sample size, and sigma is the population standard deviation. Now, that's a good thing to know, but we want to start to take these ideas about sampling distributions and answer questions like, suppose we have an estimate. If we took a different sample, how different do we think our estimate would be? So we would like to know a numeric value maybe of this. The problem is it depends on the population characteristic sigma that we don't know, okay? So we have to estimate the population standard deviation, all right? If we're working with a sample mean, we have this sigma in the numerator. We don't know the value of the population standard deviation, but it makes sense to, in place of that, maybe use the sample standard deviation S. Okay, so instead of sigma over root n, we would maybe use S over root n as an estimate. All right, what about the sample proportion? Well, we know in that case the population variance or standard deviation sigma, square root of p times 1 minus p. Of course, we don't know the value of p, okay, because we don't observe the whole population, but it would make sense to maybe just plug in our estimate of p into that formula and treat square root of p hat times 1 minus p hat as our estimate of the population standard deviation, okay? And then similarly for regression, you may remember that regression standard deviation of the slope estimator involves this term, sigma sub u. That's the standard deviation of the error term. We don't observe the values of the error term, all right? We don't observe the whole population. What we're going to do is use the sample standard deviation of the residuals, which is something we can calculate as an estimate for this object, okay? So a standard error is what you get if you go to the standard deviation formula for an estimator and you plug in an estimated value, okay? It's an estimated standard deviation of a sampling distribution. Okay, so for example, for the sample mean, I would write this at SE now instead of SD, standard deviation, standard error. All right, instead of using sigma over root n, we don't know sigma, we're going to use the sample standard deviation S over root n. All right, and that's what makes it a standard error. So this thing right here is an estimate of the unknown true standard deviation of our sampling distribution. All right, I put a table right at the end of the slides here to try to show you for the three estimators we've talked about, means, proportions, and regression slopes, okay? Basically to try to reinforce the idea that a lot of the concepts here are in common across these cases, and then maybe the table can also help you, see the differences. So in every case, we have a population parameter we're going after, whether it's a mean, proportion, or slope. And then we have an estimator for that, a sample mean, sample proportion, slope estimator, okay? Under random sampling, is our estimator unbiased for any sample size? Yeah, for the means and proportions, it is. For regression, maybe, if we want to think of it as just a descriptive analysis, or we're analyzing experimental data or something like that, then it could be unbiased. Okay. The standard deviation, we've derived all these formulas or presented all these formulas before. What I want to highlight here is that each of these depends on things that we don't know in the population and needs to be replaced by estimates that we can get from our data, okay? And when we drop in those estimates, we go from the sort of true but unknown standard deviation of the estimator to a standard error for our estimate, okay? So standard error, standard error, standard error. All right. And the central limit theorem says for a large enough sample size, all of these estimators, the shape of them across possible samples will begin to be normally distributed. All right. Again, as the sample size increases.